have just recorded the stabilographical signal of the adolescent subject. Let's load another signal into the program to compare the characteristics of two signals. For convenience, I can hide the data loading area. These charts display signals frontal and sagittal components. After loading of stabilograms, they could be analyzed. The first way of analysis is a spectral analysis and calculation of stabilogram spectrum curves characteristics. This display shows the spectral curves of the loaded signals. The blue curve corresponds to the spectrum of the first stabilogram and the red of the second. Using this cursor, you can find out the exact values of the spectral density of the signal at any frequency. Here are these values. Here are spectrums corresponding to the frontal components of signals. It can be switched to the sagittal components. Using these controls, one may set the frequency band for which the characteristics of spectrum curves are calculated. And here one can set the percentage for calculating the dividing frequency. Here are the values of spectrum curves characteristics, the dividing frequencies, and the standard deviation within a frequency range for each stabilogram. This table shows the spectrum curves peaks ordered by decreasing of spectral density values. There is a possibility of spectrum curves averaging. Okay. At last, one can save the current charts to a file. The following way of analysis is the construction of surfaces reflecting changes of the spectrums in time. The left surface corresponds to the given component of the first signal and the right of the second. For easier surfaces comparison, color filling of the surfaces is carried out using a common scale. One can set the frequency range and time interval of interest for detailed surfaces examination. Images of these surfaces are also can be saved to a file. For the detailed studying of frequency components temporal dynamics, there is a tool for drawing charts of spectral density and evolution surfaces slices along the frequencies of interest. This method is more convenient to identify the relationships between the components of the signal. The fourth way of stabilograms analysis is the construction of wavelet representations of signals and their binary variant. One can set the initial time and the number of detailization levels which will determine the parts of the signals which will be analyzed. Here are the displays with the wavelet diagram and its binary representation and the correspondence table between frequency values and wavelet diagram level numbers and the fields with threshold values for which one can construct the binary wavelet diagram. Each level of the wavelet diagram shows the coefficients corresponding to a certain frequency, which can be clarified using this correspondence table. For drawing the binary diagram, it is necessary to set the thresholds for each detailization level. To do this, one must use an additional module which calculates and stores the threshold values for a given sample of signals. So, let's load the sample of signals, name it, and start the calculation of the threshold values for this sample. Okay, the file with the thresholds was created. Now it is possible to load calculated threshold values and build the corresponding binary diagram. Here are the controls for maximum and minimum levels of detailization for the signal's filtration. Changing their values makes it possible to filter out the given signals. On this tab, one can examine the filtered signals. On this tab, one may examine the signals in the specific frequency bands and store various patterns corresponding to normal or pathological states of subjects. Let's save some patterns for further comparison and recognition. This fragment will be pattern 1, and this fragment will be in another frequency band, will be pattern 2. Okay. It is possible to compare accumulated patterns with fragments of the signal. These charts show the selected fragments of the signal under study, and these charts show the selected pattern. We can compare these fragments sliding this cursor. Having a number of pathological patterns, one can perform the recognition procedure. Let's choose the length and frequency band of available patterns and start the recognition. After recognition process, the names of recognized patterns and their positions in the signal are displayed in this and these indicators. Finally, to ensure the accompanying statistical analysis of stabilograms, spectral densities, the characteristics of spectral curves and the wavelet coefficients, the export of these data could be implemented. Before export, one can set parameters of calculation such as coefficient of spectrum's averaging or frequency band for spectral density surfaces, and then start the export. I briefly talked about the all capabilities of the developed software. As you remember, during the demonstration I saved a few pictures as well as performed the export of the signal's characteristics. Let's look at the results. This file contains the full details of the subjects, the initial signals, estimates of the spectral density of the signals, the values of spectrum evolution surfaces, as well as the wavelet coefficients. These files store the spectral densities of signals, the characteristics of spectral densities, as well as the wavelet coefficients for a given sample of subjects. And here are the saved images which may be useful for researchers as an illustrations for the preparation of articles. That's all. I wish you liked this demonstration. Thanks for your attention.